So good morning, dear student. Last class we were discussing about Ruth Hurwitz's criteria, how to construct Ruth Hurwitz's table, and how to interpret the table, and how to comment on the stability. So last we have seen this example where we were finding the range of K for which the system is stable. Which condition we have applied? We have applied that the first column there should not be any sign change. If there is a sign change, that directly gives us how many roots are there to the right half of the S plane. Okay, so based on that criteria of Ruth Hurwitz, we commented on the stability and also we found the range of values of K. We have one more example for the same case one. This is what the block diagram given. You have to construct the characteristic equation. How to do it? So this is what the closed loop unity feedback loop. First you have to convert this to a single block, that is C of S by R of S you have to compute, and you will get a characteristic equation that is denominator of this transfer function. Okay. So once you can get this transfer function, we can start writing the Ruth table. So how to take the first row of the Ruth table and second row of the Ruth table. So Ruth Hurwitz's table, first and second row, we fill it based on the characteristic equation coefficients. Okay. So S power 3 is the first row, that is the highest degree of the characteristic equation. So I have to take the coefficient of S cube as the first element, that is 1. I should skip S square. I should go to S term coefficient, which is 31. I have to take it, skip the next term, and there is no other term we have taken here, 0. Second row, I should look into the characteristic equation, that is coefficient of S square, that is 10. I have taken here, and I should skip coefficient of S. I should take the next, which is constant 1030, which I took it here. Okay. So now 1030 and 10, they are huge numbers, huge number. So you can take a common out and you can cancel. Okay, you can divide this entire row. Ruth Hurwitz, any row you can divide by any constant, which is not affect the stability of the system. So we can do that. So here we are dividing the second row by a constant 10. So I have the first element of the second row is as 1 and second element as 1 or 3. See, we are just trying to avoid having bigger number because later we have to compute determinants to fill up the Ruth Hurwitz table. Okay. So third row is S power 1. Decreasing order we have to take it. So this is a third degree equation. So you will be having 4 rows here. Okay. S power 1. First element, how we can find out? So it is the determinant of first and second column, that is 1, 1, 31, 103 with a negative sign divided by the second element of the first column, that is 1. So which leads to minus 72. Similarly, I can compute this, which is first column and the last column. Since the last column is 0, so you will find that this term vanishes, that is 0. So when this is not there, this definitely will not be there. Okay. So S power 0. How to compute? You have to take this element and this element, and you have to consider this 103 and 0. So if you take that, minus of that determinant of this divided by minus 72, which is equal to plus 103. And this term according to the formula, we will be getting 0. Now, how to comment on the stability? I should look into the first column. What is the first column here? This is the first column of the Ruth Hurwitz table. I have first element as plus 1, second element as plus 1, third element as minus 72, and fourth element as plus 103. So how many sign change happening here? Sign change from here to here, we found that plus has become minus, and from here to here minus has become again plus. So what is the inference? In the first column of the Ruth Hurwitz table, we found 2 sign change. twice the sign change happened. That is 1 to minus 72 and from minus 72 plus 103. So you could see that the sign change happened twice. So we say that there are two roots to the right of the S plane, hence the system is unstable. Okay, so very simple, we conclude case 1 with this, that is first column elements you will not find 0. That was the case 1. So that is very easy for us to fill up the table. We will go through the criteria, Rutherford's criteria, that is we will check in the first column, is there any sign change? If there is no sign change, it is stable. If there is sign change, we will see how many sign change, that many roots are there to the right of the S plane. So next is we have one more example with S power 4, okay, S cube 3S square 5S plus 10 equals 0, okay. So we have to construct the Rutherford's table, okay. Very simple, how we will do it? So we will take first and second row filled by characteristic equation itself, coefficient of S power 4, that is 2 first element, coefficient of S square, that is 3 second element, and the constant 10 I have here. S cube, the row S cube, first element coefficient of S cube itself, that is 1. I should not take this, I should take coefficient of S, that is 5. And after constant, we don't have any term, we have 0 here. So I have to compute S square. How we could compute? It is 1 into 3 minus 5 into 2 divided by 1. So that's what we have here, which leads to minus 7. Okay. And how to compute this? How did I get this 10? So 1 into 10 minus 2 minus 2 into 0 divided by 1. That I got it as 10. Okay. What is S power 1? According to the formula, it is minus 7 into 5 minus 1 into 10. We have this divided by minus 7, which is equal to plus 6.43. Okay. And the other two element is 0. So finally S power 0. How I could compute this? 6.43 into 10 minus 7 into 0 divided by 6.43, which is equal to 10. Okay. So this is what we will be having the Rutherford's table. Now how to comment on the stability? We will see that how many sign change. You can see here plus 2, plus 1, minus 7, plus 6.43 and plus 10. So you can see that here from plus 1 to minus 7 there is a sign change. From minus 7 to plus 6.43 there is a sign change. Totally there is 2 sign change. Okay. Since there are 2 sign change happening in the first column of the Rutherford's table, system found to be unstable. System found to be unstable because there are 2 sign change. There are 2 roots to the right half of the S plane. The system is unstable. Okay, so now we will go to case 2. Okay, case 2, what we find is we will find the first column prime element is 0. That is, first column first element will become 0. If first column first element 0, then next row element we cannot compute because that will become the denominator of the next row element computation. So we will be getting infinity, which is not correct, which is not admissible in the Rutherford's table to comment on the stability and to look for the sign change. So what we do is we have 2 solutions to this problem. One is, first what we do is, first solution we say that instead of having 0 in the first column first element, we will take a very small positive value, that is epsilon. Okay, we take a very small positive value epsilon and we will continue constructing the table. Okay, that is one method. Other method is we will construct the characteristic equation by reversing the coefficient. Okay, reversing the coefficient, we will construct the characteristic equation. That is how we construct the inverse of that system. See, once the system, you have characteristic equation to the left half of the S plane, then by doing the reverse coefficient method, you will be finding one more system. That system roots also will remain in the same domain. It will not change. Okay. By reversing the coefficient to whatever the roots you will be getting, they will not cross the quadrant. They will not cross the quadrant, so that we can say that stability of reverse coefficient system and the stability of the given direct system will be same, because by reversing the coefficient you will not find the roots moving to the other quadrant or the other side, or what we call it as right of the S plane. So we have two procedures here, we can adopt any one. So first what we have seen, that is replacing the zero by a very small positive number epsilon. Okay, and we will try to complete the table. Okay, so let us take up an example. Okay, we have a characteristic equation of order 5, s power 5 plus 2s power 4 plus 2s power 3 plus 4s square plus 11s plus 10 equals 0. This is what the characteristic equation we have. Now we have to construct the Rutherford table. So as I know that the first and second row we will fill up by looking at the coefficient of the characteristic equation. So as I said, alternating terms we have to take it s power 5, we have to take it as 1, 2, 11. That is the coefficient we have in the first row. For the second row, left out the coefficient, you should take it in a sequence 2, 4, 10 I have. So third one we have to compute. So how to compute? It is 2 into 2 minus 4 into 1 divided by 2. So while computing that, you will find that 2 into 2 minus 4 into 1, you will get to 0 in the numerator. That 0 divided by 2 will be 0. So you get at this position 0. As we have seen that if I get a 0, then next row element I cannot compute. So what we have decided here? We have decided to take a very small positive value which tends to 0. We will take it here and then try to complete the table so that we can observe if there is any sign change. If there is no sign change, we declare system stable. If there is a sign change, we declare system unstable. So now by doing that, we can easily calculate the next row element. Okay, so this one we got it as 0, we replaced with an epsilon, a very small positive value. Now next element as such, there is no problem in computing, we got it as 6. Now we have the question how to compute C1. So C1 according to the formula, it is 4 into epsilon minus 2 into 6, that is 12, divided by epsilon. This is what we have according to the according to the formula we have. And how to find d1? D1 we will find based on the C1 value which we have here, that found to be 6 C1 minus 10 epsilon divided by C1, which gives us the value 6. Okay, where C1 is what? Minus 12 by epsilon, which we substitute here, and we will compute the D1 value. Okay, so now if you look into the first column element, the C1 value becoming minus 12 by epsilon. Okay, what value it takes, not important, sign is important. So we have minus here at the C1 position. Okay, D1 is positive, and last one we have a constant 10. So here you have one sign change at C1. Okay, there is a C1 element becoming negative. So totally we count there is a 2 sign change, because epsilon we take it as positive, C1 we found it as negative, D1 positive. So we take as 2 sign change. From epsilon to C1 there is one sign change, and from C1 to D1 there is another sign change from minus to plus. So we have 2 sign change, 2 roots are existing to the right of a base plane, system is unstable. Okay, this is what the remedy we have by replacing the 0 in the first column element, we are replacing 0 with a very small positive number epsilon, and we continue completing the Rutherford table, and we look for the sign change and we comment on this step. Similarly, we have the same case extended, and here we are trying to find the range of k for which the system is unstable. Okay, I repeat, determine the range of parameter k for which the system is unstable. What is the transfer function given? It is s power 4 plus s cube plus s square plus s plus k. The root array of the above characteristic equation is, shown below. Here we have a root array or root table, we call it as. First two rows we will fill up based on the characteristic equation. I'll take s power 4 coefficient 1 and s square 1 and k I'll be taking, that is I'll be taking alternate terms coefficient, and for s cube I'll be taking s cube row, I'll be taking 1 and there is no term, so 0. So now I'll be computing a square row. So here we get a 0. That 0 we replace with epsilon. And second term we got it as k. Okay. So how to compute C1? C1 is equal to C1 is equal to epsilon into 1 minus k into 1 divided by epsilon. So that leads to minus k by epsilon. This is what we will get. Okay. So now, the values of k greater than 0, the system is unstable. Okay. Values of k for the system greater than 0 is unstable because it's becoming negative. For negative values of k, it will become positive, system stable. Okay. So for all the values of k greater than 0, system is unstable. For all the values less than 0, system is stable. Okay. So range of values, if I want to, if we are trying to give, then this sign change we don't want. So we want positive value for this term. So positive value when you get when k becomes negative. So when k becomes negative, that negative values of k get cancels with this minus, explicit minus what we have, so system becomes stable. And when the system is unstable for all positive values 0 and above, the system is unstable. Okay, answer is for all values of k 0 and above, the system is unstable. So we have here the next example. We have s power 5. That is fifth order of equations we have. So we will go with the first table here. The leftmost, there is one table, you just observe that. So we will try to fill the first two rows of the table. So how can we fill up the first two rows? So s power 5 is the highest row here we have. So highest power is s power 5, coefficient is 1. Pick up the next alternate number for the next element of the row. Pick up the next element here for the next element of the table, and we don't have any element after this 5, so we will stop. So 1 3 5 are the coefficient, and the missed coefficient here we will be taking in sequence, that is 2 6 3 we will be taking in the second row. So this is how we will fill up the first and second row of the root Hurwitz table, and the third row is s power 3 row, we have to compute. So while computing this s power 3 row, the first element is becoming 0. What to do? Replace that 0 with the very small positive value epsilon. We have taken epsilon here and we have computed the other elements here. That is, I got here 7 by 2 and here I am getting 0. Okay. And again, based on this epsilon 7 by 2, we have computed this term and we have tried to fill up the table according to the formula which we have discussed. Okay. So now what is the question? We have to determine the stability of the closed loop transfer function, correct? So to determine the stability, I don't want any sign change in the first column of the Hurwitz table. Okay. So we have to now see that there should not be any sign change happening. Okay. So you have to see the table here. So is there any sign change happening? We have to see, and then we have to conclude. Okay. So what we say is we can assume for epsilon very small positive or very small negative values. Okay, based on we will get the sign change. Okay, based on that we can get the sign change. So we have the option of assuming epsilon becoming a very small positive, or you can assume epsilon to be very small negative value. Okay, so if I assume epsilon to be a very small positive value, then this is having a positive, this is positive, epsilon assumed to be a very small positive now. So this term becomes negative. This term becomes negative because this is very small, this is very small. I'll be having -7. So, I'll be having minus here. Okay, and we have a next term here. Again, this term is positive. This term becomes positive. Okay, so we have here plus. Okay, substitute epsilon 0 and c. Okay, if you substitute epsilon 0 and c, then you will see that you will be getting -47 by -14. So you will be having some value which is positive. Okay, finally lastly it is positive. So there is only one sign change happening. So since there is one sign change happening, the system is unstable. Not one sign change happening, only this term is becoming negative. So there is two sign change. So +2 minus and -2 plus. So twice the sign change happening. So system is unstable if you consider epsilon to be a very small positive. Similarly, you can consider epsilon to be a very small negative number. You can assume that if you do that, you will see that epsilon you have assumed to be a very small negative number. So you have minus here, and rest of all the term, these two terms will become positive. Okay, and you can see that there is two sign change. There is two sign change happening. So system is unstable. So what is the conclusion we have to draw out of this table? So first column element sign change is very, very important to comment on the stability. While replacing a 0 by a very small value, epsilon, you can assume epsilon to be a very small positive value, or you can assume that to be a very small negative value. That is not going to affect the analysis of the stability in the Routh-Hurwitz table. You can assume epsilon to be a very small positive or a very small negative. You will find the number of sign change remains same. Okay, so number of sign change found to be two roots to the right of the S plane. So system is unstable. The question is answered because we have to comment on the stability here of the system. So we found that the system is unstable, two roots to the right of the S plane. And additional information what we have learned here is you can assume epsilon to be a very small positive value or a very small negative value. Stability is not getting affected. Okay, so next is what the other solution to the problem, that is instead of assuming an epsilon you can go for a reversing of the coefficient. Okay, so we can find the polynomial that has the reciprocal roots of the original. It is possible that the Routh table for the new polynomial will not have a 0 in the first column. Okay, I repeat, here a polynomial that has a reciprocal roots of the original polynomial has its roots distributed the same. I repeat, a polynomial that has the reciprocal roots of the original polynomial has its root distributed the same. So as I said, root distribution will not change. For example, in the original polynomial, if you have two roots to the left, two roots to the right, and one root on the imaginary axis, then if you are constructing a reciprocal system by reversing the coefficient, you have constructed the reciprocal system, and those roots distribution remains same. That is two to the left, two to the right, and one pair on the imaginary axis. The distribution pattern will not change. Okay, so number of roots to the left side, number of roots to the right side, and number of roots on the imaginary axis, that's what we call it as distribution pattern, will remain same. We use that concept and we will try to have a reciprocal system constructed. Once the reciprocal system is constructed, that first element becoming 0 will be can be avoided, and we will not find that situation. So we can continue completing the Routh-Hurwitz table for that reciprocal system. Okay, that what we call that is reversing a coefficient, whatever system we have constructed, we call it as a reciprocal polynomial or polynomial to a reciprocal system of the given system. We will complete the table and we comment on the stability. because we know that the root distribution for the reciprocal system and the original system is same. So this is what proved by Phillips in 1991. We follow that in solving the difficulty which we encounter, that is the element becoming zero. That difficulty we can resolve by doing this. Okay. Now let us do it. That is resolving this problem using the reciprocal system construction. Okay. So same example is taken. That is example 8. That is 10 divided by s power 5 plus 2s power 4 plus 3s cube plus 6s square plus 5s plus 3. Same system we have taken. So now we have to construct the reciprocal system. How to construct the reciprocal system? You keep s power 5, s power 4, s power 3, s power 2, s power 1 and s power 0. You keep this s term in its place. Pick up only the coefficient and place them in the reverse order. So that's what we have done it in constructing the reciprocal system. Characteristic equation 3 has come first, 5 has come next, 6 has come third, 3 has come fourth, 2 has come fifth, 1 has come last, sixth. Okay. So this is how we will be constructing the reciprocal polynomial, and we'll try to construct the table. Routh table construction, I need not explain again. The Routh-Hurwitz table construction procedure, which we have discussed already, we have to construct, using the formulas as we have discussed, and you have to complete the table. So accordingly, what you found that there is one sign change happening. There is one sign change, sorry, two sign change happening, because 1.332 minus 1.75 we have, minus 1.75 to 1 we have. So twice the sign change happening. So system has got two roots to the right of a base plane. So system is unstable. So whatever we have done through epsilon method, we got the same stability comment. Now we have, reciprocal polynomial constructed. For this procedure also, we got the stability same. Okay. So that's the conclusion we can give. Okay. So the case 3 I'll take up in the next class. That is entire row becoming 0. How to handle this situation? We will see in the next class. Okay. Thank you all.